As an example of derivatives of exponential functions, we're going to take a closer look at Newton's law of heating and cooling. And we're going to start the story this time from a very different perspective, and this will also help motivate why the function that we've seen in chapter 1 takes the particular form that it does. So recall that if we have an object with temperature U of t. So we have an object that has a temperature that's allowed to change in time. So U of t represents the temperature of our object. And this object is placed in a room with ambient temperature equal to R. It's an E. Ambient temperature R. So ambient temperature is basically the temperature of the surroundings. So Newton's law of heating and cooling says that U of t is going to be given by R plus, and we get this constant R minus U sub, actually it's the other way around, U sub 0 minus R. It has to be the other way around. U sub 0 minus R times e to the minus kt. So here U sub 0 is the initial temperature of the body. So this is the initial temperature. So we've seen applications of this before. For example, a hot cup of coffee sitting in a cold room, or a frozen turkey placed into a hot oven. How does the temperature of the body, whether it's a hot cup of coffee or the cold turkey, change in time? And we use this general equation to describe the temperature as a function of time. Now, it should be noted that there are a few modeling assumptions that go into this, and the first one is that the ambient temperature is a constant. So since there's conservation of energy, and when a hot cup of coffee cools, it cools by exchanging thermal energy with the environment. So thermal energy leaves the coffee and gets transferred to the surrounding air. Technically, it does increase the room temperature, but it's such a negligible amount. So the assumption is that you're in a room large enough so that any heat exchange between the body and the ambient, the room temperature, is negligible, so we can assume that the room temperature is a constant, right? So if you have a cup of coffee that's 200 degrees Fahrenheit and you set it on a table and you come back the next day, you wouldn't expect to open the door and say, wow, it's 200 degrees in here, because the coffee will be room temperature, but the room temperature today versus yesterday will be unperceivable difference between the room temperature. So we'll assume the room temperature is constant. In other words, you're in a large enough space that even though you're giving energy to the environment, it absorbs the energy without any appreciable change in its temperature. Now, where does this actually come from? Well, this comes from something called a differential equation. That's supposed to say differential. I'll just change the n here. Differential equation. So a differential equation, and there's an entire class devoted to this that you would normally take following Calculus 3, perhaps after linear algebra as well. And differential equations are similar to algebraic equations. So when you have an algebraic equation, you're looking for an unknown variable. So for example, x is some unknown variable. You have an equation that involves x, and then you solve that equation to solve for x. With a differential equation, instead of having an unknown variable, you actually have an unknown function. So the differential equation would have an unknown function U of t. So this equation star would not be known. But you have some sort of equation that relates the function to its derivatives, and that relation is called a differential equation. So I'll show you how it comes about here. So Newton's law of heating and cooling itself is actually a differential equation that describes how the temperature of a body changes. So Newton's law of heating and cooling actually states that the rate of change of the temperature of the body, So the rate of change of a body's temperature so in this case it would be the derivative of u with respect to t, du dt. So the rate of change of the body's temperature is proportional to the difference, the temperature difference between the body and its surroundings. So in other words, du dt, which is the rate of change of the temperature, du dt is going to be proportional, so we need a proportionality constant, which we'll call K, and then the difference between the body's temperature and the room temperature. So the derivative of the temperature should be proportional to the difference between the body's temperature and the room temperature. Now, there's only one extra thing that we have to take into account here, and that is that we get the sign right. So by convention, let's assume that K is positive, because that way we can just, in our mind, we think of K as a positive number. So if K is to be positive, do we need to add a minus sign out front? Well, to answer this question, we have to rely on our physical intuition. So let's do some examples. If you have a hot cup of coffee in a cold room, so the temperature of the coffee, so the value of U is going to be much greater than the temperature of the room. So U minus R will be positive. A 180 degree cup of coffee minus a 70 degree room, that's going to give you a positive number. So the right hand side would be positive. But that's not right, because du dt has to be negative, because a hot cup of coffee in a cold room isn't going to get any hotter. It's going to start getting colder. It's going to eventually approach the room temperature. So since the coffee is cooling, the derivative of its temperature needs to be negative, indicating that the temperature is decreasing in time. So to fix this, we need to put a minus sign. Now we also want to check this other case, if the body is colder than the room temperature, to make sure this still works. You know, maybe it's a case where you need a different sign convention for the two cases. So now let's think about a frozen turkey that you place into a hot oven. So the turkey might initially have a temperature of 30 degrees, and the oven might be 350 degrees. So 30 minus 350 would be a negative number. So whenever the object is colder than the room temperature, U minus R is negative. So this quantity would be negative. The minus sign out here is negative. So when you multiply the two negatives together, you get a positive number, indicating that du dt is positive, resulting in U increasing, right? The derivative is positive, the function is increasing. So this works correctly either way. So du dt is minus K times the quantity U minus R. So that is Newton's law of heating and cooling. I think I can, okay. So in differential equations, you actually solve this differential equation to derive this function up top. But here, since we haven't developed the tools yet to study differential equations, I'm just going to show that this equation up top actually satisfies the differential equation. So in other words, if I plug in this function into this equation, it works. So to do that, I need the function u right here, and I need du dt. So to do this, I need to take the derivative of u of t. So u prime of t, well, the derivative of r is 0, and then we have, so we just have to take the derivative of this part. Well, this is a constant coefficient. It's just u0 minus r. u0 and r are constants. E to the minus kt. K is a constant. So it's an exponential function, so with a base e, so we rewrite it. So the coefficient up front, u0 minus r, nothing happens with that. Actually, let me save some room. Let me put it like there. u0 minus r is like that. E to the minus kt. So with an exponential function, I just rewrite the exponential function, e to the minus kt. And then I multiply by the derivative of the exponent. So the exponent is minus kt. K is a constant. The derivative of minus kt is equal to minus k. So I'll move the minus k up front. So u prime is equal to minus k, that's a k, not an r, minus k, times u0 minus r times e to the minus kt. So minus k like that. Okay, so now let's look at the right-hand side. So the right-hand side is minus k times u minus r. Well, u minus r, well, here's a plus r, so when I subtract r, I just get minus k times this. So minus k times u0 minus r e to the minus kt. So you'll see that u prime of t actually equals minus k times u minus r. So where this formula comes from is it's the unique family of equations, given these parameters. So for different values of u0 and r, you get a different equation that satisfies this relationship down here. The derivative, the rate of change, is proportional to the difference between its current value and the room temperature R, right? So if you have a 70-degree room and a 130 cup of coffee and a 100-degree cup of coffee, so 70-degree room, 1 cup of coffee is at 130 degrees, another cup of coffee is at 100 degrees. So the temperature difference on the second cup is only 30 degrees, and the temperature difference on the first cup is 60 degrees. So since the temperature difference on the hotter cup is twice the temperature difference on the colder cup, at that moment in time, the hotter cup should be cooling twice as quickly as the cooler cup, right? Which makes sense, because if you're at 500 degrees and you're in a cold room, 500 degrees is something really hot and it's going to give off a lot of heat. But if you have a room that's 70 degrees and a cup of coffee that's 71 degrees, well, its temperature won't be changing that fast because it's such a small temperature difference. So it's basically that temperature difference that drives the heat transfer, and it drives the heat transfer in a rate proportional to the temperature difference. That's basically the underlying principle behind Newton's law of heating and cooling. So previously we saw and explored this function, so now you can see why that function is the way it is.